Again, my name is Sergey Maschenko. I'm from SharkNet, based at McMaster University. Today's topic is survival guide for the upcoming GPU upgrades. More total power, but fewer GPUs. Here's the outline. The plan is to spend the next, say, 40 minutes or so walking you through my slide deck, covering the following points, such as what problem are we trying to solve, what are the possible solutions, and I'll be talking about CUDA streams, MIGs and MPS. I will tell you how to pick the right solution, and at the end, there should be time for live demonstration. So what exactly problem are we trying to solve today? Let me step back a bit and start from a very basic law of parallel programming. It's so-called Amdahl's law. Here you see the expression. This is the equation to compute what would be the speed up of your sequential code if you parallelize it. There are only two parameters here. P is the fraction of the serial code which is parallelizable, and N is the number of processors. Could be CPU cores, GPU cores. So you can easily see what's happening here. As you increase number of processors, N, this expression is convergent to a constant asymptotically. Important assumption here is that the problem size you're trying to solve is fixed. As you increase number of computing cores, the speed up increases for a while and then becomes constant. So there is a wall, there is a limit how much you can speed up your code if the problem size is fixed. Here's the visualization of the Amdahl's law. So you can see this behave asymptotically convergent to a constant. And let's consider the optimistic case. Let's say you have a code which is 99% of this code is parallelizable, only 1% is not. So P is equal 0.99. And as you can see from this table, realistically, if the problem size is fixed, again, you can use maybe up to 50 CPU cores or so. If you, for example, try to increase up to 100, you will be wasting 50% of CPU cycles, which is not acceptable. So realistically, it's something like 50 or so. So from the Amdahl's law, if you take a computational code which used to run reasonably well on an older, smaller GPU, by well, I mean it was utilizing pretty well, let's say 80% or high utilization, and then you just move it to a modern, larger GPU. I'm kind of saying might, but in fact, almost for sure, you will see a code performance, much worse performance, and utilization of the GPU will be much worse. Most likely, most of GPU cycles will be wasted. And this is because the problem size now is too small to saturate this large, massively parallel GPU. As a side note, this is not going to be the real suggestions in this presentation, but one possibility to completely sidestep this issue of problem size too small for modern GPUs, if you follow so-called Gustafson law. So Amdahl's law is basically strong scaling. You fix problem size, and that obviously puts a severe limit on how much speed up you can get, or how many CPU or GPU cores you can usefully use. In Gustafson laws, this is a weak scaling scenario. As you increase number of GPU cores or CPU cores, you should also increase the problem size accordingly. For example, if you're doing CFD, computational fluid dynamics, you might want to increase number of cells. If you do n-body simulation, you might want to increase number of n-body particles proportionally. And if you do that, then from theoretical Gustafson law, which is idealistic supercomputer with essentially zero parallel overheads, like zero latency, infinitively large bandwidth, then your speed up should go up, increase indefinitely. As you increase number of CPU cores or GPU cores, speed up should increase indefinitely. In real life situation, it never happens. There are real life parallel overheads. So at some point you will hit a wall, and even your performance may start decreasing as you increase number of computing cores. But overall, you should get to much higher number of CPU or GPU cores. Again, this is a side note. This probably will not apply to most of you. Often you have a specific problem to solve with a modern large GPU. So this is not the solution. A sort of orthogonal way GPU programs can be very wasteful to utilize very small fraction of the GPU, and we do see such jobs on our clusters, is if you have a program which consists of highly parallelized segments of the code, original code, which use GPU very well, but these are separated by long gaps of GPU being idle or almost idle, because there is just not enough of parallelism in those parts of the code. This results in a bursty utilization of the GPU, and this can be as bad as small problem size. If you average over the time of your job duration, you will see very low utilization of the GPU. So what problem are we trying to solve today? On our national systems, we have a relatively small number of powerful, expensive GPUs. So we have a huge demand for GPUs, more so than for CPUs. For example, for our national annual research allocation competitions, we typically have twice more oversubscription for GPU requests versus the CPU request. So we have to cut back accordingly by the same factor, which is very unfortunate. And to add insult to injury, even now, many, maybe most GPU jobs have low GPU utilization. They're only using a fraction of a GPU. I'm going to be showing you some slides and also live view of Narwhal cluster, where you will see we typically have significantly less than 50% of the GPU cycles utilized across all GPU jobs. A way to solve this problem is to somehow share a single GPU between different processes, either belonging to the same user or between processes of belonging to different users. And NVIDIA does provide technologies to achieve this. There are a few ways to get them. But now also question, why now? What about the timing? Why not 1 year ago? We already had this problem a year ago, right? Why not 1 year in the future? Timing is kind of critical now. The problem of underutilizing modern large GPUs will become much more extreme when we will upgrade our national systems in the next 3 to 4 months. So what's going to happen? Our old GPUs, P100, V100 will be discarded. Instead, we will install much newer current generation H100 GPUs. The important side notes, Narwhal cluster will not be upgraded this time, so all of its 636 A100 GPUs will stay as they are now. So here there are both good news and bad news. The good news, after the upgrade, the combined compute power in GPUs will grow very nicely by a factor of 3.5. So here I'm using our special units, RGU, reference GPU units. On my next slide, I will explain a bit more what it means. But currently we have around 6,000 compute power RGUs, and it will grow to around 21,000 RGUs. But the number of GPUs will actually go down substantially from 3,200 to around 2,100. This will exacerbate the problem we already have with inefficient GPU jobs. So if we, you users, don't do anything, if you just take your jobs and move to new clusters, new H100 GPUs, the GPU utilization will become much worse, and things like long queue wait time will become even more extreme for GPU jobs. So something needs to be done, and I'm going to show you today how and what can be done. This is the RGU. This is the units we just made them up for convenience. It's a way to express a power of GPUs we have or plan to have. This is the full list of these GPUs using a single number. We assign somewhat arbitrary weights to HPC performance metric of GPU, AI performance metric, and also memory, how much memory it has. In these units, one is basically P100, V100 is 2, A100 is 4. And you can see how a big jump it will be, the transition in the next 3 months. We're going from 4 to 12.2 H100 by more than a factor of 3. Or compare 1 to 12 for those of you who are still using P100 GPUs. So this will be a huge transition. We must adapt to this new situation by adjusting our workflows. Otherwise, it's going to be a disaster. All right, so in 4 months from now, this is going to be the landscape of the GPUs on our national system. As I explained, Narwhal will stay as is right now, but the 3-4 cluster national system will have upgraded GPUs. So Cedar will become Fir, Beluga will become Rorqual, Niagara will become Trillium, and Graham, we still have to make a new name for it. And all of them will get new H100 80 gigabytes GPUs. Another important piece of information here, in the new systems, this is going to be ratio of GPU per CPU core and GPU per host memory. These parameters will become important later on. So we will have a range between 12 and 24 CPU core per GPU, and between 124 and 256 gigabyte per GPU of the host memory. So this is the snapshot. It's not the worst, not the best. Just when I was preparing this presentation, I went to Narwhal cluster portal. I will show you later how to do that. It's extremely useful resource and essential for this presentation. And it shows you what was the global GPU performance across all the GPU jobs within 7 days. So what you need to compare the orange line, which is the allocated GPUs. There are around 600 of those. These are all H100 GPUs. And you need to compare those with the blue line. This is the actual GPU cycles utilized, expressed in whole GPU units. So you can see here, most of the time we are between 30 and stretching to maybe 50% utilization. So around 60% or so GPU cycles are already wasted on Narwhal. A bit later in live demonstration, I'll show the current snapshot. I'm sure it's not going to be better. Sometimes actually it looks worse. And imagine what's going to happen if you take all these jobs and just move as is to H100 cluster. This blue line will shift back by a factor of 3. So utilization will be instead of 40%, something like 15%. So completely untenable, unacceptable, and also the queue wait time will become even longer. So just untenable situation, unless we change the workload for our users, or users will change their workloads. So let's switch to solutions. What are the possible solutions? This is not really a serious solution for this situation, but I'll mention anyway. I'll have a couple of slides for CUDA streams. This is the oldest technology from NVIDIA to share unrelated tasks on a GPU. It's been around since the first days of CUDA. A CUDA stream is a queue of GPU-facing commands, kernels, memcopy, memory allocation, etc., coming from a single process. When you declare more than one stream, then you can send different GPU operations to different streams, and they may run concurrently if resources permit. So biggest drawback for this presentation, this is limited to a single process. So you cannot run unrelated things sharing on a GPU. And as a consequence, if the problem size of what you're trying to solve is too small for modern GPU, CUDA streams will not help you, will not save your day. Another significant drawback, you need to be a CUDA programmer to even consider this. And most likely, if you're using a well-developed modern GPU code, it already has all the streams built in. So it's already squeezing out the last bits and flops of GPU performance by utilizing streams. But again, if your problem size is too small, it's not going to help you. I'll give you just one example where streams can be useful. Consider two situations. Here on the top, we have the green operation. So we need to copy large vectors, say, to a GPU from CPU. This is the green area. And this is followed by a red area. This is the kernel computing, processing those values. So now we can improve situation with efficiency by explicitly introducing two streams. One is a copy stream, and the other one is execution stream. So as long as this problem is data parallel, which means results do not depend on basically order of execution, you can split up your long vector into a bunch of segments. And then as your kernel is processing the previously copied segment, you are simultaneously in a parallel stream copying the next segment of the vector. So this way, you can hide a very significant cost of moving data from CPU to GPU. This is the biggest bottleneck for NVIDIA, at least GPUs, copying the data through slow PCI bus. You can speed up this part of the code by almost a factor of 2. But this was more of a side note. Let's now focus on the two main technologies we'll be focusing on today. These are MIG and MPS. The great advantage compared to streams, neither of these approaches require rewriting your code. In fact, your code doesn't even need to be recompiled. So these are very easy to use and test and implement technologies. So there are two methods. One is a static way of fragmenting a large modern GPU into a bunch of virtualized GPUs. This technology is called MIG, multi-instance GPU. It's available fairly recently since Ampere generation. So right now, only Narwhal cluster has such GPUs, A100. The other technologies has been around longer since Kepler generations, for example, K20. And this technology is called MPS, used to be called HyperQ. MPS stands for multi-process service. This technology, unlike MIG, which is a static way of segmenting a GPU, results in dynamic workload sharing and balancing between different processes which try to share a single GPU. So from purely theoretical point of view, dynamic workload sharing should typically result in a better performance and better utilization. But we'll get to that later. Both approaches have their pros and cons. So your code might benefit from one or the other one, or both. In fact, this might be most of current jobs might benefit when you use both technologies together. And there are some corner cases when neither technology will work, and I will touch upon that as well. So let's talk a bit about the MIG technology. As I said, you take a GPU, you split it up into virtual GPUs. Each of these virtual GPUs is obviously smaller. So you assign certain amount of multiprocessors, compute power, and certain amount of memory for each virtual GPU. Because there is a nice virtualization happening here, a MIG approach is particularly useful for applications that require high degree of isolation security, like financial or healthcare industries. MIG approach has a relatively low level of granularity. Okay, that's the word I was looking for. Granularity is relatively coarse. You can split up basically into 8 segments. So memory split into up to 8 equal size segments. And compute is also split up into 8 segments, but one out of 8 is not available for MIG. So there is an overhead in terms of computing power. So you're losing around 10% of your GPU compute power. So each instance has dedicated memory and processing. And because of this low or coarse granularity, there is only a limited set of compute plus memory configurations. We call them MIG profiles. So let's consider H100 GPU first. So the total list of possible profiles is listed here. And the name of the profile consists of 2 numbers. First number is how many computational segments out of 7, basically, or 8, depends how you count. And it goes from 1G to 2G to 3G to 4G. And 4G is basically 1/2 of the original GPU. And the second number gives you just the amount of memory, 5 GB up to 20 GB. On Narwhal, right now, there are only 2 profiles available, 3G 20 GB and 4G 20 GB. We may change that in the future, but for now, only 2 are available. And it is extremely easy to switch your job script from using full-size GPU to use a MIG. So at the very bottom, this is the line you use for full-size GPUs. To switch to use a MIG, what you do, you add underscore to the GPU name and put the profile name, either 3G.20 GB or 4G 20 GB. And then, as usual, you say how many of these MIGs you need. So what about H100? It's the same number. It's a segment divided by 8, similar as A100. So the profiles are quite similar. The only difference, twice amount of memory, because the total amount of memory is twice larger than A100. And we have not decided yet which profiles to make available, but I strongly suspect we will have the full spectrum of H100 profiles from 1G to 4G, for the very simple reason that even 1G is already more powerful than current P100. It's roughly 1.5 or something. So let's switch gears. Let's talk about the second technology. Let's talk about MPS. As I mentioned before, theoretically, one should expect a better utilization of GPU or one using MPS versus MIG because it's dynamic workload balancing. And here's a demonstration on the right side. Look at this plot here, and imagine there are 3 processes, A, B, and C, which are trying to share one single GPU. So the timeline goes down. So initially, you can see the orange A process required more compute cycles than the other two, and it got what it wanted. Later on, it's the opposite situation. It's the process C, which needs more compute power, and the other two need less power. And this all nicely balances out in this dynamic workload balancing situation when you use MPS. So you can see there are no gaps in this example, no point in time when GPU cycles are wasted. Of course, in real life, it's not as simple as that, but on average, MPS should result in better utilization, as long as your jobs qualify for MPS. I'll say more about that later. Typical examples where you want to use MPS, for example, you have a code, MPI code, where each rank uses a GPU. So now what you can do, you can enable MPS. I'll show how. And then basically you instruct a group of MPI ranks to share a single GPU. No changes to your code are required. This is all achieved by just doing adding a few lines to your job script. Another typical situation where MPS is used or can be used is GPU farming. When you want to share GPU between multiple instances of a code. Think of Monte Carlo simulations. You do parameter sweeps. So anytime you need to run more than one or a few instances of your code, MPS would really be helpful. Unlike MIG, where you need to add one line or maybe edit one line of your job script, with MPS, you probably need to add a couple of lines. For completeness, I'm showing the top line here, but this is the way how you kill MPS daemon. Usually don't need it unless you play with this interactively using salloc to allocate a node. But normally what you put in your job script is the expert command shown here, and then the command which launches the MPS daemon. So what is a daemon? It's just a fancy name for a program which immediately goes to background and just lurks there in the background, waits for the user processes to request the GPU, and then it basically handles all the GPU requests and sends it to GPU to basically achieve maximum possible utilization of the GPU. Granularity of MPS is substantially better than with mix. Remember, mix is only 8. We go in segments of 1/8. Here it's up to 48 processes can share a single GPU. So there is more flexibility there. You can deal with much smaller problem size codes. Unfortunately, there is a catch. So for mix, it was computing overheads. For MPS, it's a memory overhead. It is for H100, it's 432 megabyte plus the execution copy, the binary copy on the GPU for each process. So you have to multiply up to 48. So you can end up using a large, significant chunk of the GPU memory. This is important here at the bottom. MPS is perfectly fine to be used with mix. And in fact, I suspect this is where we are heading. Maybe many or most of user jobs will be doing that. Let me show how you use MPS for GPU farming. And this is the example I'll be showing in a live demonstration. So you request your compute node with a GPU. In this case, it's A100. And you need to request at least as many CPU cores as the number of clients number of instances of your code you're going to run in this job. Then you launch the daemon, MPS daemon is shown in the previous slide. And then you can use bash for loop. And then you as shown here, you can launch multiple instances of my GPU code. Here we redirect our output to uniquely named files. Two important aspects here. So this is ampersand, which means these jobs go into background right away. And also it's important to use wait command that forces the script to wait for all the background jobs to finish before it moves on. If you forgot to put wait, your job will die almost instantly without computing anything useful. So this probably will work fine for most situations, but there might be some corner cases where you will want some finer control over how much resources different clients or different processes sharing single GPU can use. So let's first talk about provisioning the compute resources. This can be achieved by setting up an environment variable, CUDA MPS active thread percentage inside the job script. The default value of this variable is 100%. which means any MPS client can use up to the whole GPU, up to 100%. If this is not good for you, you want to limit how much percentage compute can be used by individual client, you set to some other value, let's say 50% or 40%. It's important to know that over-provisioning is permitted. So the sum across all MPS processes may exceed 100%. This is fine. This is just upper cap. What's the highest percentage of the total GPU is allowed to be used? Probably slightly more useful, more frequently used, the way to provision memory. Apparently, there are some codes. I was told PyTorch, maybe one of them, which tend to cannibalize all the GPU memory it can grab. So if you try to launch MPS and the very first instance of your code will grab all the memory and then the rest will get nothing. So for those special situations, there is a way to limit the memory. You can do it either per client, for all clients, the same value. You do it inside your job script after you launch the MPS daemon. And by the way, this is the way to pass the arguments to daemon once it's running. There is a long list of other arguments you can use. Here's just one example. I use echo, then the name of the argument and the values for the argument. So we set default device pin memory limit at 0 is the MPS server ID, which will always be 0 in our examples. And here we're setting the limit to 2 GB for all clients sharing the GPU. If you want to be more specific, there is a way to do that using environment variable inside the job script. And here indexing corresponds to MPS clients, the order of their launching. So if as you launch your clients, your processes inside the job script, the index 0, 1, 2, etc. And then you can assign individual memory limits per process. So here's the summary, side by side, MPS and MIG. I'm not going to be talking about streams anymore. Let's focus in on maximum number of partition. So granularity is much better for MPS. So you can deal with a wider range of problem size, including very small problem size. MIGs are more limited in that respect. But again, you can mix the two technologies. As I will show at the end, you typically will want to do that. So you basically use both technologies. Memory protection is yes for both, which is good. In terms of error isolation, MIG has it and MPS doesn't. So if that is critical for your application, then it pushes you towards MIG as opposed to MPS. So let's discuss how to pick the right solution. First of all, the obvious question, does your code need this? I think the answer is yes, pretty much. As you've seen already, the current GPU utilization narrow is pretty bad already. So pretty much everyone using GPUs will have to test the GPU utilization to see, basically to do the analysis I'll be showing in the rest of this presentation. And that's important. GPU utilization depends not only on the code you're using, but very strongly on the problem size. Remember the Amdahl's law? So even if you use your code before and it worked reasonably nicely, and then you started using for some other problem, you have to retest this because problem size changes and this needs to be retested. And testing is very easy and straightforward. I'll be showing you shortly. There was one exception. If your code needs more than half of the GPU memory, you can't share it between more than one process, obviously. So you cannot use MPS, you cannot use MIG. It doesn't mean you can get away with it. If your GPU utilization is very low, I will give you a strong recommendation at the end of this presentation. So you still need to do something. It's an important change to your workflow. So here are a few steps you should do to test your code and to choose the right technology. The very obvious step number one, you have to measure the GPU utilization. And it's done very easy now using the Narwhal portal, cluster portal. I'll show you how. So if you go to our documentation site, search for the cluster name, let's say Narwhal, then go to the cluster page, and at the top there will be a portal link. For now, it's available on Narwhal, but for the upgraded systems, I was told it will be available for all of them. And then you have to come up with a relatively short version of your code, which would run a few minutes, maybe half an hour, something which would realistically cover all these If you have bursty behavior, you want to cover all of that in that test run. And then you use Portal to see what was the utilization, resource utilization of your job. And it's very easy to do. I will show you. And these are the qualifications. So if your job requires less than 50% of the GPU memory and has, it's somewhat arbitrary, 75% threshold. Basically, we consider things below 75% utilization as bad, above it's reasonably good. So if it's below this threshold, that you should test your code with MPS first, then MIG, and perhaps both. Optionally, if you discover the GPU utilization is low, and if you're curious what kind of situation is going on, whether it's a small problem size or maybe it's a bursty GPU performance, you may want to do profiling of your code. And the best profiler for NVIDIA GPUs is NSight. It's a GUI application. It's already installed on all clusters. Because it's GUI, you either need to use VNC to compute node, which is a little bit cumbersome. I think most of you will find much easier to use Jupyter Hub. This is a web browser-based interface to run GUI application on all clusters. Look for details on this wiki page. Once on your compute node, you have to say module load CUDA, and that makes available two NSight profilers to you. We're mostly interested in the high-level profiler, it's so-called NSight systems. But if you're a CUDA programmer, you may want to also consider NSight Compute. This is a low-level line-by-line code profiling, individual kernels. I did a webinar on profiling GPU codes with NSight and a couple of years ago, and it's available on our YouTube channel at youtube.sharpnet.ca. You may want to check it out. I have two toy code examples in my live demo part. There is a bursty code example. I will not be testing it today, but I show you how it looks like under NSight Compute. So, and I'm paying attention to multiprocessor utilization, this line. As you can see, utilization is close to 100%, but it comes in short bursts. So overall utilization is poor, but inside the burst, utilization is close to 100%. The problem I'll be demonstrating live demo today is a small problem size example. As you can see, the utilization is consistently very, very low, just single digits. You can barely see the thickness of this orange line. So that was step one. Now step two. Let's first consider MPS. I gave you theoretical grounds that MPS may be more efficient if important condition is met. And this condition is that you need to run enough of these instances of your code to actually make use of it. For example, if you need to do job farming with large enough number of instances to saturate the GPU, or if you're running MPI code with GPU acceleration. So in other words, if it's the opposite situation, if you just need to run one GPU job which doesn't use MPI, the MPS is the wrong tool, and you skip to the step 3. There is a side note, your job script may already be using MPS. Chances are very small. I'm giving you just one reference I found on our documentation site, PyTorch GPU MPS.sh job script, where it's explicitly using MPS daemon. And the only thing you need to do with MPS is to test a few test runs, test jobs, changing number of clients, how many MPS clients per GPU to get a nice saturation level. The full range is between 2 and 48. And the upper limit will probably be set by other factors. You may run out of either GPU or CPU memory first before you hit 48. And also remember, there is a relatively low ratio CPU core to GPU between 12 and 24. And you typically want to have a dedicated CPU core per process to get the best performance. So this limits number of clients you can use under MPS. And as you do a few tests, you don't need to test all the MPS client values, just test a few and pick the smallest number of clients, which will make GPU utilization 75% or better. If that doesn't apply to you, if your job, you just don't have enough of MPS, of instances of your code to justify using MPS, then consider using MIG. There is a side note how to look for, make sure there is enough of memory. By the way, on the previous slide, I didn't mention that it's also important memory. If you run out of memory, there will be memory crash, but probably more useful thing, not to wait until you get a memory crash. You can use a portal, cluster portal, and it will tell you what was the GPU or and CPU memory utilization. And by changing number of clients, you can see where you're approaching the 100%, and then you stop there. For mix, you want to choose the profile which will fit your problem, your code. Again, you can use the portal to see if you're approaching the limits of memory. Just repeating the information which profiles currently available on Narwhal, only 3G and 4G. The future systems will likely have all the profiles. Important side note, if you're using MPI plus GPU code, then you have to use equal size mix for your job. And the goal, again, here to try to get to 75% plus GPU utilization. And what about combining these two technologies? I suspect it will be the case for many jobs. You will have to combine both. First of all, it's perfectly fine to use MPS on a MIG. The only thing to remember, as you decrease the size of your GPU effectively by using MIG profile, the number of clients you can run is reduced accordingly. Instead of 48, you can be able to use only up to 24 or 18, 12, or 6, depending on the size of the profile. And here's the guidelines why you want to consider using these technologies, two technologies together. For example, you tested MPS and you get very nice utilization with MPS. But to achieve that utilization, you need to run, let's say, 12 instances of your code, and you only need to run 6. So you just don't have enough of instances to saturate GPU. The obvious solution is, instead of full GPU, you use a half-size MIG, let's say 4G profile. And the same number of clients will now be able to saturate your GPU, your MIG, as I will show in live demonstration shortly. The other point may be actually more critical. We haven't really decided yet, as far as I know, but it's likely that we will have most of our H100 GPUs will be split into MIGs. So there will not be too many full-size GPUs. And that means MIGs will be much more available. And so the queue wait time will be shorter if you combine MIG with MPS versus using MPS on a full-size GPU. So this might be the most important factor to consider to shorten the queue wait time. And if not everything else fails, let's say your code needs lots of memory and utilization is still very low, then you should consider switching to CPU-only version of your code, because it's just not going to be acceptable when GPU is using a small fraction of GPU cycles just because it needs lots of memory on the GPUs. This code looks like it just does not belong to GPUs. Test the CPU version of this code, and chances are you'll get not much worse runtime, and maybe you'll get shorter queue wait time because you now run it on CPUs. All right, so switching to live demo. And what I'm going to do, here's the web portal for Narwhal. You have to log into a portal using your CCDB Alliance credentials. There are lots of things you can do, but just to show you what's the current state of the Narwhal utilization, I'm going to click Scheduler here. So you can see right now situation is kind of worse than what was showing you before. So total number of GPUs available is slightly above 600, but utilization is 260, 270. So we're definitely using less than 50% of GPU cycles. For CPUs, it's not as bad. Again, comparing orange to blue, so we're using maybe 70+% of CPU cores. So they're substantially bad. For GPUs, it's already bad. And then imagine on H100s, you take the same jobs, move to H100s, the blue line moves down by a factor of 3. That's how bad it may get. So to do the live demonstration, here's my terminal. I just logged into Narwhal cluster. I created directory MIG, no, I think it's MPS_MIG. I made it readable. So after this presentation, you can go ahead, log into cluster and copy the whole directory with the toy code examples and job script to try it out yourself. As I mentioned, there are two toy code examples, primes, HQ. This is the small problem size example. Both examples search for a largest prime number in a given interval using brute force approach. And the burst example is primes burst. But for today's presentation, I'll be just using this example. All the tips for the live demonstration are in the tips file. So these are the things you want to put inside your job script to launch MPS daemon. And this is the job I'll be running today. In fact, I want to start it now because it may take a while to run the job. The runtime is 2 minutes only. So what I'm gonna run, the first example is using this job script. I'll show it in a second. It has takes two arguments. One is the path to the binary. This is the code I'll be using. And this is the number of MPS clients. So when it's 1, it's basically I'm not using MPS at all. And this job script uses full-size A100 GPU. And then I'll run it with 12 clients. And then I'll run it with 24 clients. Then I'll do the same with the MIG. So this is 4G MIG. It's half size of the A100. So again, I'm going to run just not using MPS at all. And then I'm going to use, because it's half size of A100, I have to use twice fewer number of MPS clients just to keep it consistent. So I'm going to use 6 and I'm going to use 12. As you can see, most of these jobs are already running. Runtime is around 2 to 3 minutes. And so while it's running, I'm going to show you the job script. The job script is shown here. Here, the first 3 jobs are using full-size A100 GPU, 30 minutes runtime. My code doesn't use much host memory, so it's 40 gigs for everything. And because I'm testing with up to 24 MPS clients, I'm requesting all the 24 CPU cores. These are commands I need to do to launch MPS daemon. And then I'm running this script and I'm timing it. And the reason I made a separate script because you may want to play with it interactively. You just do salloc and then you just run the script by itself. This script takes again the same 2 arguments, the path to the binary and number of MPS clients. So let's see what's inside that script. And that script looks exactly like one of my slides. This is the for loop. So I'm running my second parameter is number of clients. So that many instances of my code. This is the ampersand to put this in the background. And this is the path to my binary. And I'm making sure there is a wait command so my job doesn't die prematurely. So let's see what's going on with the jobs. So, okay, so out of 6, 1 finished running. So let me switch now to the portal and I'll start showing the job statistic. So to see individual job statistic, I'm going to this tab, job stats. I'm scrolling down to individual jobs. So this one just finished running and no, in fact, 1, 2. So, okay, these 2 already finished running and the other 4 are still running. So the very first job I submitted was full-size GPU, not using MPS at all, so 1 client. So what's the performance? The job is fairly short duration, and sometimes there is not enough data to generate plots. So in this case, CPU plot is not available. These measurements are done typically every 30 seconds. My code is 2 minutes long, but still the CPU cores sometimes are not shown here. This is the host memory, very tiny utilizations, not a problem. I'm scrolling down to GPU utilization. So as you can see, there were 2 time measurements. The final was here. So GPU utilization is extremely poor. It's only 7.4%. It's basically wasting virtually the whole GPU. It's a very bad utilization because I know the problem size is too small. That's why it's happening. If you're curious about how much GPU memory used, it's all available here. And as you can see, it's a very small amount of memory being used. So let's switch to the second job, which was, okay, 3, and then 3. So this one, I had 12 MPS clients. So now it should be, okay, again, CPU wasn't measured properly. You need longer test job to see that nicely. But my main focus on GPU utilization. And you can see how much nice it is now. From 7% by using 12 clients, I pushed it to almost 89%. So it's very decent. It's perfectly acceptable GPU utilization. In terms of GPU memory, it's still quite low, so it's not a problem. And then what about the third scenario? 24. So we're kind of pushing the limits. 24 is probably not realistic because remember the CPU core to GPU ratio is typically under 24 for most of our upgraded system, just for the heck of it. So now there was enough of data to measure CPU utilization. So you can see all 24 are doing something. They're busy. And then moving further to GPU utilization, it's at extreme, it's almost 99%. So it's extremely good utilization, but there is some caveat I'll show in a second. The memory is still not a problem. So let me switch back to my tips. So here what I'm showing are the runtime of the whole job. My original code just running by itself is 2 minutes runtime. Utilization is horrible. By using MPS on a full-size GPU, I maintain the same runtime and reaching a very nice utilization. So this is pretty much the answer. This is what I want to use. This is how I want to use my code. When I push to extreme 24 clients, things improve in terms of utilization, but not dramatically so. But look, the runtime started increasing. It almost doubled. So in terms of GPU cycles, it's almost no difference. So runtime to result become longer. So you have to wait twice longer. You are overusing, you're using more than your fair share of CPU cores per GPU. So you're not, and only gaining a little bit of utilization, GPU utilization efficiency. So the best option is here. I'm not gonna be showing the actual live results for the second group of 3 jobs, which are using half-size 4G MIG. I'm just gonna discuss the results here. So when you run the same code on a half size of the A100, runtime is obviously the same if there is no MPS. The performance, relatively speaking, is twice bigger because the virtual GPU is half of the size of the original GPU, so no surprise here. When we use 6 clients, we still have the same runtime and performance reach very nice 86%. So this is a very good result. So this is what you want to use. If you need to use MIG plus MPS, this is how you want to use it. Interestingly, if you push to the limits and you run with 12 CPU or clients, MPS clients, using 4G MIG, runtime grows, okay, it's like before, but utilization goes down, unlike full-size GPU. When you combine MPS and MIG and you overcommit your number of clients, you use too many MPS clients, the utilization can actually go down because there are some overheads of MIG technology. So they're obvious here. So this case is obviously wrong. You don't want to use it. So then the answer is, first of all, this job is too small for a MIG. The things are quite linear in terms of number of MPS clients, efficiency. So if you instead of if you use 1G, for example, MIG versus full size, so then you basically gonna be, so let me find example. Here, it's 14%, it's 4G. Let's say you want to use 1G, which is not available. I cannot test it, but my estimate should be 4 times longer. 4 times high utilization. So it's gonna be around 50% or so, right? Which is not good enough. So even 1G is too big of a virtual cluster for this small size problem. So for this particular case, you really want to use MPS somehow, either with the full size GPU or MPS plus MIG. That's maybe going to be the most common situation for most of you. All right, so this was the end of the live presentation. I'm going to switch back to my slides. Here's the main takeaways for this presentation. There are already lots of inefficient GPU jobs on our clusters, and your job is very likely one of them. This results in long queue wait time and also in very bad utilization of very expensive hardware, very poor values for taxpayers. The situation will get much worse after the upcoming cluster upgrades. Despite increased combined GPU compute power, the queue wait time will become longer and utilization will become much worse. Unless you change the workflow, and this is how. Fortunately, the 2 NVIDIA technologies to share GPU, MPS, and MIGs can fix the situation, and they are very easy to use, as hopefully you've seen from my presentation. So here are the references I used for this presentation. Most of them are public domain. And then only one of these is you need to have an NVIDIA developer account, which is free, but maybe a bit of a pain to get through. And thank you very much for your attention.